I'm Johnny Adams. Today I'm interviewing Dr. Bill Lawrence. Dr. Lawrence is an American biogerontologist. He has a PhD in nutritional science, an MS in psychology, and a law degree from the University of California, Los Angeles. For 3 decades, his focus has been on human longevity research and interventions for optimal life and health span. Dr. Lawrence has been affiliated with the St. Petersburg Institute of Bioregulation and Gerontology in Russia since 2015. He is the administrator of 2 Russian and American longevity clinical studies, telomerase activation and DNA methylation modification. These studies use peptide bioregulators, developed during the last 40 years by Professor Vladimir Kavinson, the director of the St. Petersburg Institute for Human Organ Regeneration, Mortality Reduction, and Reversing Human Biological Aging. Professor Kavinson and Dr. Lawrence have developed a peptide longevity program that regenerates human organs and systems, significantly reduces human mortality, and reverses human biological aging, as measured by several tests. His presentation today will include the scientific data and evidence supporting the peptide longevity program. Chronologically, he's age 76, but his biomarker ages measure younger, and he has the energy and vitality of a much younger person. Dr. Lawrence, we know you were an entrepreneur and an attorney. How did you evolve into a scientist working on such innovative age management therapies?
Well, hello, Johnny. That's an interesting journey. I'll try and be very brief. I was raised in a religion, the Mormon Church, where they do a lot of genealogy work. And I knew as a young man that most of the men, and actually almost every man in my family line on my father's side, died in their 50s and 60s, almost everybody from heart disease. And in 200 years of history where we had, not every data point, but we had enough birth and death information covering 200 years that there was only one man that actually made it to age 70. As I say, everyone else died in their 50s, 60s. My father had his first heart attack at 57, and a fatal myocardial infarction at 64. So knowing that, that was always sort of in the back of my mind. And then when my father died at 64, I was in my early 40s, I guess, at that point. And I was doing the entrepreneurial things. I was building medical buildings and shopping centers and a whole slew of things. And I thought, I need to reorganize my priorities, because is it worthwhile earning another $5 million and passing it on to my children? Or is it more worthwhile for me be able to live beyond what our traditional family history had been? So it was a matter of disposing of everything, shopping centers, et cetera, going back to school, getting the PhD. And then 30 years or so ago, I started this trek as a researcher, specifically for longevity interventions that had evidence behind them. So that's kind of the story. Unfortunately, 3 of my siblings, I came from a large Mormon family, 11 children. 3 of my siblings, all in their early 60s, have already died at this point. So it's a very real issue for me. So with that, Johnny, if we're ready, I am going to start talking about the peptide program that we've put together. So, Johnny, we've been running these clinical studies. The Professor Kavinson and I, the telomere study started about 2015. So we're at 7 to 8 years at this point. we have amassed a large amount of data showing that with the peptide bioregulators, which I'll explain in a little bit more about, that we can actually lengthen telomeres. And doing so is one of the biomarkers for at least suggestive of a biological age reversal. And I'll get into more detail about that. The second study, called the DNA methylation study or epigenetic study, is about 3 years old at this point, started just barely before COVID. And it's looking at using the peptide bioregulators to modify DNA methylation, which has a significant impact on longevity, and I'll explain that as well. So the program, these two clinical studies are sort of the foundation for a program that we've created called the Peptide Bioregulator Protocol. In other words, the studies that we've been doing and collecting the data are evidence that the peptides can be very effective. And now what we've done is developed a protocol, or in other words, you can now use this program in order to reverse your biological age, for organ regeneration, and for mortality reduction. It is a program that anyone can undertake now with lots of evidence behind it. As I say, the peptide longevity program consists of the two clinical studies. They're the foundation of the program. And the goal is enhanced lifespan, reduced mortality, organ regeneration. All of those things are possible. And I'm going to present hard evidence as an attorney and as a scientist showing that those things can be done. As an attorney and now as a scientist, this is very true. You have to have the data. There's lots of people out there talking about this intervention, this product, this vitamin, et cetera, is going to do wonderful things. The first thing I want to know is, well, do you have human clinical studies proving that that is in fact the case? And unfortunately, 99% of the time they don't. At best, they have maybe some animal studies. Animal studies are not good enough because very few animal studies actually transfer over to human application. So it's got to be human evidence, human clinical studies. We have both published clinical studies as well as 7 to 8 years worth of data supporting this program. So it's clear, this is what sort of I was looking at some years ago. As Steve Jobs says, it's clear that the most precious resource we have is time. And when I was a tax attorney doing a lot of estate planning and so forth, I would have people come in who had amassed a certain amount of wealth. And we would talk about, their plans and their family and so forth. And I would always pose the question to them, if you could get another 10 or 15 years of healthy living, what is that worth to you? And I had one man make it very clear to me. He was worth probably $10 million at that time. He said, I would give away all of my wealth if I could have 10 more years. He was in his early 80s at that point. In other words, it's much more important to have time than have money. So the two programs are the telomerase activation and the DNA methylation. A client sent this to me because all of us engage in this kind of activity. In other words, we try and hold the clock back. We try and slow it down. And that's a very valuable thing to do. And that's primarily what most aging interventions do, is they try and slow the passage of time, keep people healthy as long as possible. I have been engaged in this kind of a program for decades now, but there's now another new thing that we can do. And before I get into the nuts and bolts of it, billionaires are bankrolling anti-aging programs, healthy aging programs. The last number that I've seen is that something like $40 million has been spent by just one individual. The total appears to be over $20 to $30 billion being spent. Entire science campuses are being built that are devoted solely to the aging process and how to slow it down and how, hopefully at some point, how to reverse it. These are billionaires who have a lot more money than they have time left, so they're highly motivated. So There are three parts to this peptide program. The first is organ regeneration. The peptides can be used at the cellular level to rejuvenate cells, which then results in rejuvenation of tissue, which ultimately then regenerates the entire organ. So we could be talking about a kidney, a liver, a heart, and so forth. And the peptides, and I'm going to show you the evidence, are able to regenerate those organs. The second part of it is the peptides can create very significant mortality reduction. And there are Russian clinical studies published, numerous studies published showing significant reduction in mortality using peptides. And I'm going to show you the evidence of that. The third thing is that we can actually, using these peptides, we can reverse biological age. Now, the way we do that is by intervening with two particular what we call biometric interventions. One is telomeres, and I'll explain in a moment what that is, and the other is the DNA methylation. If we can improve those two biomarkers, that is an excellent proxy for biological age reversal. So this is the aging paradigm that we all have, pretty much. We're young, we're middle-aged, and then we are old. And with that old, we end up with the vulnerability to various diseases. And at the Institute, at the Institute, Professor Cavinson and I have a different paradigm. Our paradigm is at a certain point in life, as you see here, instead of going downhill and being vulnerable to disease and so forth and frailty, with the peptide program, we can regenerate the human being and add significant longevity to their life. And I'll show you some of the data for that in a moment. The Russians, and particularly Professor Cavinson, have been engaged in this work literally since 1973. And I'll explain some of the background in a moment. But they've been writing books, publishing clinical studies for years, using peptides as an intervention for the aging process. This is Professor Cavinson there in the middle. This is the Institute personnel, scientists, and so forth. They're in St. Petersburg, Russia. These are the people that I work with, and I have been with them since about 2015. Professor Cavinson is not known outside of Europe. He's extremely well known in Europe. In America, no one has any idea whatsoever of who he is and what he's accomplished. But he's been the president of the International Association of Gerontology for the European region, not just Russia, but for all of Europe. Served several different terms. He has published extensively. I believe that he has something over 700 clinical studies that have been published at this point. And this work with the peptides has not been confined to just Russia. The studies that were done, the clinical trials that were performed were done here in the United States with the National Institute of Aging, in Italy, Germany, Spain, etc. And Professor Cavinson basically is saying that these peptides are a system of signal molecules that regulate gene expression, differentiate cells, and increase the life-sustaining resources. What he means by the latter part of this is you end up, with the use of these peptides, adding anywhere from 15 to 20 years of healthy life to the average human being. So this is an early study. What happened about 10 years or so ago when Google Translator became available? I could now read clinical studies that have been published in Mandarin, in Russian, in French. And so I came across these Russian studies. This one is very significant because there is a limit to how much cell regeneration or replication that a human being has the capability for. Leonard Hayflick, an American scientist, very well known, received a Nobel Prize for the work he did when he figured out in the 1950s that humans could self-replicate about 40 to 60 times, but that was the max. Well, what Professor Cavinson was able to do with the peptides was increase that substantially, 10 extra divisions, 44 passages. That equates to about 30 some odd years of additional cell replication. What Professor Cavinson figured out with the peptides is that the peptides can create what we call a biological reserve of approximately 42%. And what we mean by that is, if those of you who are old enough to remember the automobiles back in the 50s, motorcycles, I had a motorcycle in the 50s, where you had a little reserve tank, a little reserve gas tank, where you would, when you were running low on gas, you would throw a little toggle switch and you would have half a gallon or a gallon or so of gas to get you to the gas station. Well, Professor Cavinson's research discovered that with these peptides, that biological reserve could be created, and that the peptides could continue to regenerate, to reduce mortality, and to reduce biological age to the extent of about 42%. And it's showing here in this graph, the average lifespan, this is from Russia and the Ukraine, this data, is 75 to 80 years. They don't live as long in that part of the world for a lot of reasons. A harsher environment. Alcoholism is a real problem in that part of the world. What he discovered was that this biological reserve equaled about 35 to 40 years, and that if you could trigger the gene expression, and these peptides do that, that you would then have the possibility of being able to add 35 to 40 healthy years, not in a nursing home, healthy, functional years. This is Professor Cavinson. He was a colonel in the Soviet Union military, and it's where this research actually started. Back in the 70s, the Soviet Union in the Cold War was concerned that because they were aware that the United States in the Cold War were developing laser types of weapons that would be able to deafen people or destroy their hearing and also blind them on the battlefield. In addition, the Soviet Union was sending out submarine crews on 3 to 4 month submarine assignments, sitting in submarines that were built in the 50s and the 60s, and sitting next to a very crude nuclear reactor with very crude protection. And what was happening is the submarine personnel were coming back with all sorts of thymus issues. Today, we would call it accelerated immune syndrome, because they were exposed to this radiation. And so the Soviet Union military, with an unfunded, a no limit funded budget, threw millions and millions of dollars to have Cavinson and other scientists do the research to figure out what could they do to basically regenerate damaged thymus, radioactive problems from the reactors and so forth. And so they went to work. Now, most people think that, I think many people anyway, think that a scientist all of a sudden one day wakes up with that light bulb going on over his head and comes up with something wonderful. That's really not the way that science works. The way that it works is you build on the research work and the scientific experiments that were done before. In other words, they call it standing on the shoulders of those before. And that was true with these peptides. Ivan Pavlov, the first Russian scientist to receive a Nobel Prize, his work was primarily, what people know him for is the classical conditioning, the gastric and the physiology and the classical conditioning of dogs. What his real work was studying the digestive system and figuring out that if you have very, very small peptides, and I'll define what that is in a moment, that you could use them to pass through the digestive system, the gastric juices and so forth, intact, and they could then permeate cell membranes and reach organs and systems and so forth, and be very beneficial for treating various organ damage. So what happened was that Professor Cavinson in the military built on the work of Ivan Pavlov and developed the whole concept much further. So they started using the peptides in the submarine force to begin with excellent results. They then expanded to the Soviet Union cosmonaut, their astronaut program as well. When the cosmonauts would come back from space trips, they also were experiencing a variety of issues, including thymus issues and so forth. So they used these peptides to regenerate the cosmonauts' health. And they expanded them to other military portions of the military. This is the Russian Olympic gymnastic team. They used them for after competitions to regenerate muscle tissue, bone tissue, and so forth. They still use them to this date. Unfortunately, Chernobyl, a major disaster, but they knew, Professor Cavinson knew that there were several of the peptides, the thymus peptide particularly, that could be very helpful with cancer patients. And so they brought many of the cancer patients who had been exposed to the radiation to St. Petersburg for treatment. And the institute there treated with a very high success rate many of those people. We call these peptide bioregulators a new class of geroprotectors. In other words, longevity interventions. And the Russians have been publishing for years now, for at least 30 years, various published studies and so forth. This one is from 2014, talking about how the peptides work in terms of organ regeneration. And a couple of years ago, about 4 years ago, President Putin awarded Professor Cavinson Russia's highest civilian award for his 40+ years of service as a doctor and as a scientist. And Professor Cavinson is saying that in his belief that peptide pharmaceuticals will become the most crucial development in the world. And we're already seeing that here in the United States, in that there are now hundreds of synthetic peptides that have been produced that can focus on particular diseases and particular ailments. In the clinical study, we use 21 of what we call the natural peptides. When I say the natural peptides, these peptides are different than the synthetic peptides created here in the US in that they are natural, extracted from 12-month-old bovines, or in other words, from cattle. They are from an animal source. They are filtered, processed very carefully, and turned into capsules for humans to swallow, injections, sublingual, and so forth. And they have peptides that they extract from various parts of the animal, that when you put them into the human being by swallowing or by injection, those peptides go directly to the associated organs. So for instance, of these 21 peptides that we're looking at here, sirtuin is the brain peptide. It's taken from the brain of a 12-month-old cow, I'm sorry. And when a human being takes that peptide in, it goes to the brain of the human being. It doesn't go to the liver, doesn't go to the lungs. And people who have had some experience with thyroid medication, the natural ones called Armour and Natrethroid in the United States, and then the generic name are Synthroids. Many people in the United States are on thyroid medication. It's the same principle, because the natural thyroid medication comes from pigs. And when a human being takes that thyroid medication, it goes to the human being's thyroid and improves the functionality of it. Well, the same is true with these peptides. So there are peptides for the lungs, the liver, the kidney, vision, the heart, the arterial system, the muscle system, etc. There are 21 of them altogether. And this is just a dynamic model of what happens. The small number of little molecules that you see on the right is the peptides. They're 2 to 3 amino acids long. In other words, very, very short. A protein is considered to be 50 amino acids or more, and some of the peptide or some of the proteins are 150, 250, 300 amino acids. The Russian peptides are unique in that there is no Russian peptide that is longer than 3 amino acids. And so what you see here is the peptide is binding with the DNA in this model and stuff. And because they are so small, they can pass through any membrane, any nuclear membrane, the brain membrane, through the digestive system, through any cellular membrane. They can pass right through and basically dock with the DNA. So what we decided was, in order to prove that the peptides could be longevity interventions, we decided that we would pick two of the most common, what we call biological hallmarks of aging. We picked telomeres and we picked DNA damage or DNA degeneration. The reason for that is that these are measurable, whereas many of the other hallmarks of aging are difficult to measure. These two, telomeres and DNA, require blood samples, which are fairly easy to do, versus the others that are much more difficult. So we use these two, telomere shortening and DNA damage, as the basis for our clinical studies. So let's start with organ regeneration. I said at the beginning that these peptides are powerful in that they can regenerate organs. Now here comes the proof. This is just a statement here by Professor Cavins where he talks about these peptides are a reprogramming technology. So no pun intended, but one of the ways of seeing how well they work is to see what happens when we use peptides for retinal issues, vision issues. And I'm going to show you a series of slides for various retina issues before and after using what we call field of vision scans. This is just one of the early studies put out by Cavinson and other scientists, unique method for restoration of retinal functions. Unfortunately, in the United States, there is basically no treatment, effective treatment anyway, for things like macular degeneration, glaucoma, retinitis pigmentosa. There are some things that are being tried that will slow down the process a little bit, but it really has minimal effect. Basically, there's nothing that can be done that is very effective in the United States. In Russia, this is a field of vision test for a diabetic retinoplasty patient. This is over a 2-year period of time. So when you look at the field of vision slide on my left, where you see a little bit of green in the middle, that means that they still have eyesight there. But when you move out from that center with diabetic retinoplasty, you see that there's yellow, there's red, and then black. That means the yellow means impaired, the red means even more impaired, the black means there's no vision at that point. 2 years of treatment with peptides over on the right-hand side. This is the field of vision test again, same patient, and this is the improvement. This patient now has a life again. The patient before treatment, was somewhat mobile probably because they had central vision, but 2 years later, they probably could be driving a car at this point. Here's macular degeneration. Same concept where you see the black and the yellow and the red in the middle. That means they don't have any, basically they don't have any vision centrally. And so you'll see people with macular degeneration who tend to turn their heads. They're looking out of the peripheral to get their vision. So over on the right, about 2 years later, significant reduction in the black and the yellow. Again, this person has certainly an improved quality of life at this point. This is retinitis pigmentosa, one of the worst kinds of vision issues. What happens with, people describe it to me, they say it's like looking through a straw, and the straw gets smaller and smaller, and then finally the straw just collapses and you have nothing in the way of vision. So over here on the left, that field of vision shows a lot of black, and it's a progressive disease. There is no intervention in the United States that can even slow it down. Over on the right, after about 2 years, significant increase where you see the green, a lot less of the black, a lot less of the red, and so forth. Again, this person has, the quality of their life has been enhanced significantly. In addition to organ regeneration, Professor Cavinson was doing studies on morbidity, in other words, reducing sick time. And so he did a large study in Siberia with Gazprom, which is Russia's large oil and gas complex. They had 11,000 employees that they put on 6 different peptides. They use peptides for the immune system, for the brain, the blood vessels, the lungs or bronchi, the liver, and cartilage. And they gave them to them in capsules for oral administration. And we're going to talk about absorption and so forth in a few moments. The control group, the non-peptide group of 3,000 employees, just took their normal vitamins and minerals and so forth. They weren't on the peptides. 1 year later, the reduction in the acute respiratory, in other words, lung issues and so forth, particularly in this toxic environment, was reduced 2.7 times in the peptide group. Total morbidity, in other words, illness from any cause whatsoever, was reduced 2.3 times. Now, that means workers were able to work more, receive their paychecks and their compensation. The employers were, of course, very gratified because they had these workers working instead of off on sick leave. But that's how powerful the peptides can be in terms of just treating common diseases. Okay, so we've talked about organ regeneration. The second part of the program is what we call mortality reduction. In other words, how to reduce the number of deaths. And another published clinical study, as I said at the outset, I require human published clinical studies as evidence. Anything short of that, except for maybe qualified data, is not going to be of much help. So this is a published clinical study in 2002. So we're talking about 20 years ago. The Russians were publishing clinical studies, peer-reviewed clinical studies, showing significant mortality reduction. And I have a summary that's coming up next of this clinical study. It just shows part of the abstract that long-term treatment with peptide preparations increase mean lifespan by 20 to 40%. Very similar to that biological age reserve we were talking about. So this is a summary of that clinical study. They took a couple of different age groups, what they called elderly people who were 60 to 74 years of age. And where you see it, where it says control, polyvitamins, that was the control group, the non-peptide group. And they just took their regular vitamins and so forth. And the next block over, circled or squared with the blue, is the use of one peptide, the pineal peptide. So let's see what the results are. They checked them at 8 years and then at 12 years. Let's look at the 12 years. So the mortality rate, in other words, the number of people who died, okay, in the control group of that age bracket of 60 to 74, 44% of those people in the control non-peptide group died during that period of time. On the other hand, in the peptide group, using only one, remember there's 21 peptides, but using only one peptide, the mortality rate dropped in half to 22%. I know of nothing out there in the world of science that comes close to that kind of mortality reduction. And if anyone listening to this or viewing this knows of something, I would certainly like to hear about it. Then we have an older group. The Russians are not very diplomatic. They call them old people. That group is 75 to 89 years of age. I'm now in that group. I'll be 77 in a couple of months. Same thing, but this time they had 2 peptides. They had the pineal gland peptide and they had the thymus peptide. So again, the control group, the non-peptide group, over a period of 6 years, we're looking down here at the bottom, because of the age of these people, it was a shorter study. But over that 6 year, almost 82% of these people died. Their mean average age was 80 going into the study. So 82% of these people died. In the group taking just the one peptide, the pineal peptide, the mortality rate dropped to 46%, 45.8%. When they were added a second peptide, the thymus peptide, when they were using both of those, the mortality rate dropped from 82% to 33%. There is nothing on the planet that I'm aware of that has any clinical study evidence behind it other than these peptides that can reduce mortality to that extent. They also use the peptides for cancer treatment, as I mentioned in the Chernobyl situation. I won't go through this whole thing. The point I want to make, if we look at the top line here, epithalamin is a pineal gland peptide. And what they were doing here was attempting to induce cancer tumors in mice. And so the DMBA is a complex of chemicals that they had the mice ingest in order to see if they could create cancer tumors. And they were successful, where you see the control where it says 81%. 81% of the mice with the chemical cancer combination complex came down with a tumor. On the other hand, the mice that they gave peptides to before the exposure and during the clinical study, only 28% of those mice came down with the tumor. In other words, very, very significant safeguarding and reduction of cancer incidence from just taking one peptide. So that's the first two parts of this. The epigenetic methylation study came about 3 years or so ago. We're hearing a lot about epigenetics. Epigenetics is basically anything outside of gene expression is considered to be epigenetics, okay? In other words, environment, toxic environments, lifestyle, diet, et cetera, would be, or stress would be epigenetic kinds of factors. So this was the second study. And as I say, what is epigenetics? It's people say it's the light switch on your genes. In other words, genes can be turned on or turned off by chemical impact, what we call methylation, and that can be positive or negative. And so what we do with the peptides is we use the peptides to turn on genes that are supporting for longevity, and we use peptides for turning off genes that are not favorable for longevity. And I just mentioned some of the factors that are epigenetics: lifestyle, diet, stress, things of that nature. This is, again, just another early study. The Russians were aware of this some 15 years or so ago, that they could intervene with using short peptides to changing DNA methylation expression. Again, another study, this one was back in 2004, as I recall. So the Russians have been aware of this. In the United States, this whole idea of epigenetics and DNA methylation modification is a fairly new science. It's probably, outside of the universities, it's probably about 5 years old in terms of the mainstream. It's now possible to do blood tests to determine an epigenetic age. And the blood tests are getting better and better, and the technology is getting better so that they can be much more exact. But outside of the university, this is brand new science. On the other hand, the Russians have been aware of it for 10 to 15 years. Professor Cavinson and several others wrote this book in 2017, some 5 to 6 years ago, explaining how peptides can control the epigenetic aging. So what's interesting about this is that we can measure and come up with basically a epigenetic clock. In other words, we can, and it's an oversimplification, but we can basically look at a human organism and differentiate their biological age, which is made up of most of their organs and systems, differentiate that from their chronological. In other words, everyone has a chronological age. Everyone has an epigenetic age. That epigenetic age, depending on what's gone on in their life, can be running faster or slower than their chronological age clock. And what our goal was to see if we could use the peptides to slow down and even reverse that clock. So this simply shows that we have the ability to, it's a crude way of putting it, but basically we have the ability to somewhat determine the age of various human organs and come up with a totality for the human being. What was fascinating is that Dr. Horvath and his team, when I say Dr. Horvath, he had about 60 scientists from all over the world working on this for years and years. What he found, though, was that if a person was aging 8 or more years faster than your calendar age, that you then have twice the typical risk of dying compared to your same age peers. So if you were 70 years chronologically, but having a blood sample test done, a DNA methylation test done, epigenetic test done, and you, let's say that you were 77 DNA wise or epigenetic, your all-cause mortality risk just doubled at that point. The other side of that is if you were 7 years slower or less than your chronological age, you have half the percent exposure to death. So we use that in these scales. So this is a graph showing if a person has a epigenetic age more than their chronological age, they have an increased mortality risk. And it's not nearly as linear as I have it here, but it gives you the idea. So if a person, let's say, is 5 years older epigenetically than their chronological age, they have a 62.5% increased risk of all-cause mortality compared to their same age peers. On the other hand, if a person has a decreased mortality risk because their epigenetic age is younger than their chronological, so let's pick a person here 4 years younger, the individual has a 28% reduced risk of all-cause mortality. In the clinical study, what we did was we tested people for baseline DNA or epigenetic age. And then our goal was to get as many people as possible down into this decreased mortality risk. And the optimal goal was to get them down to 7 years less than their chronological. We had people, and I'll show you some of the labs in a moment, we had people who were 15 years older on their baseline epigenetically than their chronological age. And over a period of time, we were able to bring them down to 2 or 3 years older. That is a significant, significant reduction in all-cause mortality. So Professor Horvath, again, what he was saying here is it's great that we can measure this, and which is wonderful to be able to measure it. But he says, I don't really see the utility of that information because we don't have a pill or an intervention. Well, we do, and that's what these clinical studies have proven. At least we do in Russia. So what we call a concept for a clinical study is we set up a trial to see if the concept made sense that we could modify epigenetic age. So over here on the left-hand side, where it says DNA age versus chronological age, and you see in the blue where it says 5.42 years, what we did was we took 9 people, because the telomere study had started 7 years ago. The epigenetic study started about 3 years ago. So we had a group of people who had been on the peptides for the telomere study for some years. So we tested them when the epigenetic age testing became viable. And those 9 people randomly picked were 5.42 years younger than their chronological age. By itself, that proves nothing, okay? But at the same time, we then took 15 people who had not been on peptides before, brand new to all of this. And when they tested, they were almost 2 years older as a group, 1.91 years older than their chronological. So what that means is they had about a 25% increase all-cause mortality risk at the beginning for baseline, versus the people who had been on the telomere study at 5.42 had about a 35% reduced all-cause mortality at this point. So 2 years went by, and we put these people on the smaller group, the 1.91, the 15 people. We put them on a peptide protocol. And 2 years later, they went from being 2 years older than their chronological to being 4.5 years younger. And again, it doesn't seem like a lot of years, but when you translate that into mortality reduction, it's staggering. And this is just a couple of the labs showing the before and afters. This is the data that if we don't have a clinical study published at this point, we're going to be publishing a telomere study later this summer. It'll be another 2 years before we publish the epigenetic study, but these are some of the lab biomarkers. So this person at baseline was chronologically 53 years of age, but he had a DNA age of 55. In other words, his epigenetic age was 2 years older than his chronological. Not so bad for most Americans come in about that number between 2 and 5 years older. At 2 years older, he has about a 20 plus minus percent all-cause mortality risk. He was in the 16th percentile compared to the population. So we put him on a program, and about 2 years later, this shows his 25% increased mortality risk. So 2 years later, we now have him at 55, and now he's at 51 epigenetically. So instead of being 2 years older than his epigenetic age, he was now 4 years younger than his chronological age. So we had changed his situation by 6 years, 2 years over and 4 years now younger. At 4 years less, he has a 28% reduced risk. So he's gone from about a 20% increased risk in 2 years to a 28% reduced risk. Another one, this is a person, he's a health professional. At 57, his DNA test came in at 72. He was 15 years older than his chronological age. That means his all-cause mortality risk was something in the area of probably 200%. I mean, this is a very serious situation for this gentleman. About 3 years later, he had aged a couple years, and we brought him down where he was now 6 years older. He was 61 at this point. His DNA age was 67. So the gap had dropped down to where he was 6 years older. His mortality risk dropped from about 200% down to 65%. Still at risk, but in about 2.5 to 3 years to reduce his risk from 200% to 65 is phenomenal. And he's still, of course, on the program. These are my results. I apologize. I'm surprised that the PowerPoint isn't showing up a little bit better. But at my baseline about 3 years ago, I was 4 years younger than my chronological age, as we saw in that control group to begin with. And a couple of years later, continuing with the program, I'm now about 10 years less than my chronological age. That translates into probably about a 70 to 80% all-cause mortality risk reduction. And this is fascinating. We now have the ability to determine a biological age, or at least an epigenetic age, of a person's immune system. And so this again is me. I was 76 when I was tested. My immune system epigenetic age was 62. And I'd been on the peptides for probably 7 years at that point. We now have the ability to actually determine a person's pace of aging epigenetically. So if 1.00 is our calendar aging, 12 months and so forth, we can now make an assessment based on epigenetic testing as to whether or not a person is aging faster than 1.00 or slower than that. This is an example of mine at this point with a pace of aging of 0.85. That translates into a 15% slower pace of aging than my chronological aging. This is a very important biomarker for us. And what we anticipate is we're going to be able to slow down people's pace of aging. It's interesting because if a person has a faster than 1.00 pace of aging, that correlates with an increase in all-cause mortality. And so in this example, if a person has an increased aging pace of 1.00 or more, what we know from the research that Dr. Horvath has done is that over the next 7 years, there is a 56% increase in all-cause mortality risk if you're aging faster than 1.00 or your calendar age. What's also interesting is within a few months, we're going to be able to not just provide an epigenetic age, not just provide the epigenetic age of your immune system, not just be able to determine your pace of aging, but as we're looking at this slide, we're going to be able to provide an epigenetic age for all of the major organs in the body. This is extremely helpful for what I do, because when I create a peptide bioregulator protocol, at this point in time, we create an overall for the organism, for the human organism. When this technology is available in a few months, I'll be able to take a look and determine the epigenetic age of a person's liver, their heart, their brain, their pancreas, etc. And therefore, I'll be able to customize further the peptide bioregulator. So if a person has an accelerated kidney aging situation, I'll be able to then use more of the kidney peptides to address that issue. We expect this to be available in about the next 2 months. So what do we do with all this information? We have people's telomere age, we get their epigenetic age, their immune age, their pace of aging, and so forth. And what we then do is I create a peptide bioregulator protocol for the next 12 months. This is an example of that. As I mentioned earlier, there are 21 of these different natural peptide bioregulators. You can see them listed here. For instance, there's peptides for the adrenals, the arterial system, bone marrow, brain, cartilage, heart, kidney, lungs, liver, muscles, etc., etc. And what we do is, in order to move the epigenetic age marker, we use most of these over the course of 12 months. And so you'll see in this example that we're using typically 5 or 6 different peptides each month, rotating them through. You'll notice then, looking down here at the pineal telomere endolutin A8, we use that peptide as well as the thymus peptide in every single protocol every single month, because they are what we call foundational. In addition to all of this, while we're not treating organ damage, diseases, etc., we don't disregard a person's health status. And so, since most of the people in the study are physicians, they provide me with any health issues that they're concerned about, and we build in additional peptides. So if a person has, let's say, some kidney issues and so forth, we will build in more kidney peptides. They have a liver issue, they have a brain issue, they have a heart issue, we will address that by adding additional peptides. And at the end of about month 13th or month 14th, we allow 2 extra months for absorption of those last peptides. We then retest at that point. So, in terms of our epigenetic study, we've talked about the telomere study. Now we're finishing up on the epigenetic study. What our results have been that over a 2-year period, that we are able to reduce people's epigenetic age by about 4.67 years. Now, we've seen earlier that we can reduce people's telomeres by 7, 8, 9 years for every 12 months on the program. And so some people will say, well, it was great you were able to change over 2 years my telomeres equivalent to 15 or 18 or even 20 years, but you only achieved 4.67 years with the epigenetic. But they are different biomarkers. There is no comparison between the two. As we've talked about previously, it is a risk reduction that we're trying to achieve with the epigenetic age modification. So with a 4.67 improvement, if a person had, let's say, 4.5 years or so older epigenetic age than their chronological age, they would be somewhere in about a 50% all-cause mortality increase risk. So if we can reduce by 4.67 years, we bring that down to zero increase risk. They have the same risk as their peers. On the other hand, if a person starts off with equivalent to their peers, but we lower another 4.67, what that means is that we have achieved about a 28 to 30% reduction in all-cause risk compared to their peers. So it's a significant reduction based on risk assessment. So the last part of this program, we've talked about organ regeneration, we've talked about mortality reduction. I've shown the data for both of those. So the final part is biological age reversal. And earlier I indicated that these studies are based on two longevity biomarkers, that being telomeres and DNA or epigenetics. So now we're going to move into the telomere section. Telomeres are simply the end caps on our chromosomes. They allow cell replication to take place without damaging the cellular makeup. Without telomeres on the end of our chromosomes, there is problems that can develop in terms of the cellular replication. If it doesn't replicate exactly 100% correctly, then there's going to be cellular issues. And the telomeres are that protective end cap. Sometimes people will compare them to the little plastic ends on tennis shoe laces. If that little plastic end cap has frayed over a period of time, it becomes impossible to lace up the shoe. It's kind of a crude metaphor, but that's the idea. They're protective end caps. And we know that when you have longer telomeres, you have less disease, you have longevity. When you have shorter telomeres, you become more vulnerable to disease. And we're going to show this in a moment. So there's significant relevance in terms of telomeres. They have to do with aging. They have to do with mortality, as we're going to look at. They also have to do with chronic disease. Elizabeth Blackburn and two other American scientists received the Nobel Prize in 2009 for her work in telomeres. We know that basically short telomeres have a relationship to all age-related diseases. It doesn't matter if it's dementia, it doesn't matter if it's heart disease, diabetes, etc. The people with longer telomeres have less vulnerability. The people with shorter telomeres have a lot more vulnerability, and there are hundreds and hundreds of studies that show this. Michael Fossel is a very bright scientist. He has written the only medical textbook dealing with telomeres that's used in American medical schools. And he says that he believes that telomerase activation is the single most promising approach to reversing the effects of aging. I have enormous respect for Dr. Fossel. We communicate periodically, but I don't think that that's an accurate statement. They're a very important part of aging, but certainly epigenetic analysis is just as important. So I think he overstates it just a little bit. This is a study that the Russians did that caught my attention as long ago as 20 years ago in 2003. And what they found was that a peptide derived from the pineal gland of a young calf could induce telomerase activity and lengthen telomeres. This is one of the studies that when Google Translator became available that really caught my attention, because I knew enough about telomeres at that time that I knew that there was a relationship to longevity and to health span. And this paper basically indicated that the Russians had figured out a peptide bioregulator that would induce telomerase activity and lengthen telomeres. So we set up a clinical study now it's been 6 years or so ago, to determine if we can use the peptide bioregulators to lengthen telomeres. And originally we had 52 participants in the clinical study. Now there's nearly 100 at this point. And we used all of the peptides, for instance, the arterial peptide, the central nervous system, the liver, the pancreas, and so forth, to induce telomerase activation. we put people on different levels of dosage, a low, a medium, and high, to determine what the impact of a different dosage would be. So now what I'm going to show you next are the SpectraCell lab data, the test data, measuring telomeres over a period of time. So this happens to be mine. The first few are my labs. And this was done when I was 66. I'm now almost 77. It was before I knew anything about the Russian peptide bioregulators. And my telomere age came in at 72. In other words, I was 6 years older. I had accelerated telomerase loss, or telomere loss. I was aging faster than my chronological by 6 years in terms of telomeres. Not a good situation. And what we do know from work done by Elizabeth Blackburn and others is that stress is likely the single most damaging factor in terms of accelerated telomere loss. And I was certainly, at that period of time, I was in my entrepreneurial period, just ending all of that, had been doing that for about 10 or 15 years at this point, had come out of a very stressful situation, and my telomeres were simply showing that up. So then 2 years later, I retested again. I don't know about peptide bioregulators at this point, and I'm now 68, and my telomeres are that of a 75-year-old. There has been a further acceleration in my telomeres situation. Then October 2015, that's when I first met with Professor Kavinson and the Russians in St. Petersburg, and began to understand what the peptide bioregulators were all about, what they could do, and had been on a program then at this point for about 8 or 9 months. So I was now 70, but my telomere age had been reduced to 68. Remarkable, because up to this point, there was nothing that would reduce, there was nothing that would actually lengthen telomeres at this point. So this was the first data that I had. The Russians had proven it years prior, but this is the first data that I had showing that my telomeres were lengthening at this point after starting the peptide program. So I continued on. 2 years later, I was 72. I continued on the peptide bioregulator program, and my telomeres were now equivalent to a 44-year-old, a remarkable, remarkable improvement. And I kept on going, using the peptides, a variety of the peptides. At 73, my telomere age was 35. And then just recently, just a few weeks ago, I received my most recent telomere test, and at age almost 77, 76 in 2 months, I'll be 77. My telomeres are equivalent to a 23-year-old man. What this translates into is the potential for significant longevity and also significant reduction in disease vulnerability, as we saw from that earlier chart. Shorter telomeres are associated with almost every major disease. Longer telomeres are protective. Then we started testing other people, of course. This is my significant other, Bess Jones. Her baseline test at age 60 indicated that she also has accelerated telomere loss. She was 63 telomere-wise, chronologically 60. I won't go through the individual slides, but then over a course of a couple of years, about 4 years altogether, at 62, her telomere age had been reduced to 33 using the peptide bioregulator program. And this is Bess. This is what at this point, she was 65. Yes, this is what a 65-year-old healthy American with a telomere age in her 30s looks like. This is Tora Bright. She's given me permission to use her name. Tora was an Olympic gold and silver medal winner. She's from New Zealand. And she had been a snowboarding competitor since she was about 5 or 6 years of age. At this point, she was chronologically 32. What happened was that the Olympic doctors routinely provide lots of testing. To my surprise, they also include telomere testing as part of their panels. What they discovered with Tora was that at age 32, she had the telomeres of a 56-year-old. And of course, we come back to the stress issue in that she had been in a competitive, highly stressful environment for most of her life at this point. So her doctor, Olympic doctor, referred her to a doctor here in the United States. The United States doctor knew the clinical studies I was running, and so he sent her over to me, and we put her on a peptide program. And it took about 2 years. And at the end of that 2-year period of time, she was 33, but her telomeres were equivalent to a 31-year-old. Significant reversal in her telomere situation. This is just a chart of the data that we accumulated. There are pages and pages of this data for the various people showing their baseline telomere length, their chronological age, showing the program low, medium, and high that we put them on, and then showing secondarily the results of a couple of years on the telomere program. So when you look at the green line box over on the far right, that's the gain in telomere age. And it ranged from just 1 year to as much as 30 years. And a lot of it has to do with the lifestyle of the individuals. Some of it has to do with the dosage levels that we had them on. The people who only gained 1 or 2 years, from what I've been able to determine, led more stressful lives, a lifestyle that was perhaps not the healthiest and so forth. And that may account for the fact that they only received a minimal amount of telomerase activation and telomere adjustment. On the other hand, those who received 20 years, 25 years in terms of telomere lengthening were going to be very healthy for a much longer period of time, given the fact that their telomeres have been lengthened so much. So the average decrease in the telomere study over a 3-year period was 21.62 years. In other words, almost 22 years. So what we were doing was, in that clinical study at that time, for every 12 months on the study and on the peptide bioregulators, we were averaging about 7 years in telomere lengthening, or you could say that were reversing people's telomere age by about 7 years for every 12 months on the program. So we've talked about organ regeneration as part of this program. We've talked about mortality reduction. We've shown you the data with regard to significant mortality reduction that the Russians were able to achieve. And now we've talked about biological age reversal. The key, though, is this, and that is what we use these peptide bioregulators for is to get people as healthy as they can possibly be as soon as we can possibly get them there. And the reason for that is that there are amazing technologies, interventions, health interventions, longevity interventions that are on the board, that are being developed right now, that some of them are actually available now. But over the next 10 years, there are astounding things. Most major diseases, heart disease, cancer, and so forth, will either be controllable or even hopefully cured in the next 10 years. So the technology is developing. The key is we've got to, the concept I use is we have to cross this longevity bridge. In other words, we need to stay as healthy as possible for the next 10 years or so in order to take advantage of those things that will be available in 10 years. Because if we do, then we should be able to leverage in 10 years another 10, 15, 20, 25 years of healthy longevity. It is therefore possible, and I think a lot of people have read in some of the medical journals and articles and so forth, that humans have the potential to live to 120, 130, some are talking about 150. The key to that is to be able to stay healthy for the next 10 years in order to take advantage of all of the developments that are either now available or will soon be available. And crossing that longevity bridge, some of the things that are going to be useful are quantum computers, artificial intelligence, which is really being birthed right now, gene sequencing, and it's going on at the moment. Stem cells, people are getting stem cells, they're getting exosomes, they're getting B cells. Replacement organs are on their way at this point. 3D printing, microbots, and so forth. All of these things will be available in the next 10 years, and we will be able to take advantage of them to extend our lives. What's happening in the science world is that biotech companies are being formed basically by very wealthy billionaires who have come to realize that they may have wealth, but they don't necessarily have longevity. And so they have invested at least $10 billion at this point in building facilities, building campuses, hiring researchers, and so forth. Some of these campuses are huge. They have multiple buildings, 100 different researchers working, and so forth. And what they're doing is doing the research that has to be done in order to come up with safe and effective longevity interventions. The problem, though, is that this is years away. That is, they've been at this for about 5 years at this point. Unfortunately, there is not a single intervention that has actually been produced that people can use today that have clinical study evidence of both safety and effectiveness. But that's the way that research works. It takes a long time of doing the research in order to finally turn that into various products, but it's on the drawing board. So, as I said earlier, this is the current aging expectation that all of us seem to have. You know, we start off young, we get through middle age, and then we reach an older age and frailty sets in, disease sets in, and we're coming towards the end of our life. I have a very different, and I share a different view of it. It's what I call the peptide paradigm of aging. My view of it is shown on this slide, where we get into, you know, the half point of our life, you know, 2/3 of the way through for most of the people. And then we apply a peptide bioregulator program. We cross that bridge that I talked about, and then we have the potential for leading healthy lives for another 30 or 40 years. I fully expect to reach at least 110 and be as healthy as I am today. Some of the background information, some of the original research, some of the original studies and so forth can be found on YouTube's. If you want that information, the detailed background information, then you can go to Bill Lawrence Peptides, and there are several interviews there that will give you all that in-depth information. What I have shown today is that we have a peptide bioregulator longevity program. Its roots started back in 1973 with the work that Professor Cavinson did. It's going on today at a much more advanced level. What we have is the only scientifically proven published clinical human studies with laboratory data that show that we can do organ regeneration, mortality reduction, and biological age reversal. If there is another program, or if there are interventions that will accomplish these things, and they have human studies, not animal studies. I don't consider animal studies very helpful at all, because too few of them transfer over to human beings. If there are studies like that, I want to hear about them. But to my knowledge at this point, this is the only program that has human study, published clinical studies, data showing that it can do these things. And with that, I am available to answer any questions that you may have. And it's been my pleasure in presenting this information to you today. I've shown today the clinical study evidence, the data that confirms that we can make a major intervention in the aging process by regeneration of organs, by mortality reduction, and by reversing biological age. The key, though, is as powerful as these peptides are, is we all need to stay as healthy as possible to cross that bridge that I talked about, where 10 years from now, hopefully the most remarkable things like heart disease, diabetes, dementia, and so forth, will be controllable or curable at that point. And that will then add an additional 10 or 15, 20 years of additional life. So let's all cross that bridge together and stay healthy.
For additional information or to join the Peptide Bioregulator program, you can contact me here.